Alright, AP Chem, here's your video lecture for Chapter 5, Section 6, 7, 8, and 9. Alright, so we're going to talk about the kinetic molecular theory for gases. Okay, there is the kinetic molecular theories in general. They refer to the other states of phase, but we're just focusing on the gases right now. And so far in this chapter, we have simply talked about what happens, those different laws, Boyle's law, Charles' law, Avogadro's law. We've simply discussed what happens and the relationships between certain variables, certain terms, and what those relationships look like. But we have never discussed why. Because in science, generally, you have to figure out what exactly is happening before you can try to explain it. So, with that in mind, we've been going over what happens. Now we're going to talk about the why. And the why is the kinetic molecular theory. So, for the kinetic molecular theory, there are going to be a certain number of postulates. Okay, certain things that need to be true, or things that are true, for the kinetic molecular theory for gases. Some teachers break them up into different numbers of postulates. The teacher that I first took chemistry with had them broken into 5, but that some people break them into 4. It simply depends on how succinct you make them. If you want to be a little bit more wordy, a little bit more specific, you can actually expand it into 5. But because your book has them stated in 4, I'm also going to state them in 4. So just don't be confused if in some place in the future, some other chemistry class, you see them listed as 5. The same information is being communicated. The first postulate for the kinetic molecular theory is that the particles are so small, the gas particles, remember we're talking about gases here, the gas particles are so small compared to the distances between them, that the volume of the individual particles, the particles themselves, can be assumed to be 0. Okay, so relative to the distance between each particle, okay, that great huge distance in between them, that is so large that the size of the actual particle is essentially nothing. It's, by comparison, nothing. All right, number 2, second postulate. The particles are in constant motion. Yeah, that's the kinetic molecular theory, right? Movement here. The particles are in constant motion, and these collisions of the particles with the walls of the container are the cause, this is the why, the cause of the pressure exerted by a gas. All right? Number 3, particles are assumed to exert no forces on each other. No forces. They are assumed neither to attract nor repel each other. No attraction force, no repulsion force at all. So if we go back to the previous slide, we look at this graphic right here, and as you pick out one of those gas particles and try to follow it as it zooms around, notice that none of those gas particles are curving, okay, curving towards another gas particle or away from another gas particle. No attraction or repulsion. They're all moving in straight lines until there's a collision. Now, if there was an attraction force or repulsion force, you would see those gas particles have to curve towards or away from another gas particle, and you do not see that happening in this graphic. That is the third postulate of the kinetic molecular theory. No attraction forces or repulsion forces in between these gas particles. And also, I would like to remind you that for a given amount of liquid that changes from the liquid phase to the gaseous phase, that same amount of liquid is going to take up about 1,000 times more volume than it did as a gas than it did as a liquid. Remember, there's a lot of expansion that speaks back to the postulate that says the relative size of the distances between each individual gas particle is so great that the size of the gas particle itself is essentially nothing. And the last one, last postulate for the kinetic molecular theory, the average kinetic energy, remember, energy of movement, moving things, the average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. And we have referred to this already in class. Whenever we do calculations using the gas laws, we have to use the Kelvin scale when we're talking about temperature. If I give you Fahrenheit or Celsius, you have to convert it into Kelvin because we're talking about the kinetic molecular theory here. And that's what the Kelvin scale is designed to do, is to help you simply talk about movement, kinetic molecular theory, the average kinetic energy of a particular object. Okay, so kind of by definition, what it's there for, it's directly proportional. They are directly proportional. Moving on, I have apparently something that's not going to work. Awesome. Alright, I guess we'll just move on and skip those. Okay, so here's something I want you to do. I want you to copy down, I want you to sketch these graphs. They don't have to be perfect, but I want you to get these general proportionalities here. I have a graph here. I have two graphs here of pressure versus volume. You have pressure on the x-axis and volume on the y-axis. And as you can see, as pressure increases, volume decreases. All right, that makes sense. And so we get this kind of asymptotal shape here on the left because they're inversely proportional. Now, if we move over here and look at the right, you notice that it's not pressure that is on the x-axis, it's the inverse of pressure, okay, 1 over pressure. And so I've made this an inverse, and so when we look at the graph now, it's a straight line, just like it was a direct relationship. All right, those aren't working. Go that. All right, so let's move on to the next sketch. I want you to make volume versus temperature. Okay, and I'm going to have you make two different sketches here, two different graphs. This one is going to be using degrees Celsius. The next one's going to be using Kelvin. But we're assuming constant pressure and moles here. The other terms in PivNert are not changing. They're constant. We're just looking at the relationship between volume and temperature. And I'd like you to notice that temperature being on the x-axis, volume on the y-axis, that there's direct proportionality here. We have a straight line, but the straight line does not start at the origin. Okay, it does not start at 0, 0. That's because we're talking about the kinetic molecular theory, and so where movement starts is at absolute 0 or 0 Kelvin, which on the Celsius scale is minus 273 degrees Celsius. And so out here is where volume becomes negligible because there's so little movement. All right, here's the graph, volume versus temperature using the Kelvin scale. Again, pressure and moles are constant, but again, we have Kelvin here on the x-axis, and so the direct proportionality does represent itself as a direct line starting at the origin. Go ahead and sketch that. Moving on, skipping that graphic because it doesn't work. One more graph for you to sketch. The relationship between volume and moles. Again, keeping the other terms in PivNert constant. We have moles, or the amount of a gas, here on the x-axis and volume on the y-axis, and they make a nice little straight line that does start at the origin. All right, here's the check for you. If you need to, go ahead and pause the video until you can come up with an answer. Be sure to justify your answer. All right, hopefully you came up with a 1-to-1 ratio. And here, let's remind ourselves what this math is saying here. The volume of neon is twice the volume of argon, okay? V equals 2V. All right, so neon is twice as voluminous as the argon here. Now, the reason that there is a 1-to-1 mass ratio is because neon is about half as massive as argon. It's about half as massive as argon. So if you have twice as much argon, the ratio of mass is going to be about 1 to 1. And if you don't believe me, go ahead and check your periodic table. All right, here's another one. You have a sample of nitrogen gas, which is N2, in a container fitted with a piston that maintains a pressure of 6.00 atmospheres. Initially, the gas is at 45 degrees Celsius in a volume of 6.00 liters. Okay, that's the situation. You have a container with gas. You have a piston that's going to make the pressure in the gas remain constant. Okay, the pressure will be constant, and it's a closed system, so the moles of the gas will remain constant. Then you cool the gas. Which best explains the final result that occurs once the gas sample has cooled? Go ahead and pause the video until you can come up with an answer. Be ready to justify your response. And I hope you picked D, the volume of the gas decreases. Again, the system was such that the piston was going to ensure that pressure remained the same, and it was a closed system, so that the amount of moles could not change. And so the only thing that can change is going to be the volume of the gas, And if there's less kinetic energy because of the cooler temperature, the gas particles are going to be moving at a lower velocity. So when they collide with the container walls, they're going to be exerting less pressure, less force, and therefore not pushing that piston out quite as hard, and the volume will decrease. Here's another check for understanding. This one's going to involve you doing some calculation here. You're going, as your hint, you're going to be using Charles' law here. The gas sample that we just talked about in that problem we just did. The gas sample is then cooled to a temperature of 15 degrees Celsius. Remember, the initial temperature was 45 degrees Celsius. Solve for the new condition being volume. What is the new volume? We just identified that the volume is going to go down, okay, in our last concept check. Now let's calculate the new volume. All right, go ahead and pause the video until you can come up with a response. All right, I hope we got 5.43 liters of volume. Again, here you would use Charles' law that relates volume and temperature. And you just use P1 T1 equals V1 over T1 equals V2 over T2, and you simply solve for the new volume. If you did that and you still did not come up with 5.43 liters, my guess is you did not use the Kelvin scale for your temperature. And you're going to have to add 273 to both of the temperatures that I've given you here, because I give you degrees Celsius. Moving on. So we've been talking about temperature as it relates to kinetic energy, kinetic motion. But what does it really mean here? Right here we have the average kinetic energy, and we have to say average because we can't really know the kinetic energy of each specific individual gas particle. It's a little bit unknowable, but the average overall, at one point, one gas particle might have collided with a highly energetic gas particle going in the opposite direction, and so it's going to accelerate, whereas another gas particle just had a glancing blow, so not a lot of kinetic energy was transferred into it. So the individual gas particles may not have the exact same kinetic energy, but overall, the system will have the same amount of kinetic energy. So we say average kinetic energy. And it's 3/2 times RT. Okay, here, that R is a universal gas constant, but it's the other gas constant. Okay, it has different units, as you can see here. It's joules per Kelvin moles. Okay, and you're going to use this gas constant when doing kinetic energy and velocity problems here. And if you're ever not sure, you have to look at the units. Okay, you have to look at the units. Is pressure in atmospheres? Are we talking about volume? So there's going to be liters in there, or are we talking about speed, some sort of energy, kinetic energy, which joule is the most common unit for energy in chemistry. So pay attention to what information you've been given, you're supposed to be using, and then make sure that those units match up. So here we have R equals 8.3145 joules per Kelvin mole. Again, a joule has a unit of kilograms multiplied by meters squared divided by seconds squared. Talking about velocity here. Temperature is still in Kelvin. But capital M here, you've seen in my class that capital M stands for molarity. It does, but it also stands for the molar mass of a gas. Okay, the molar mass of a gas. And here it's going to be in kilograms, not in grams. Okay, most of the time you calculate that sort of information in grams in my class. Here it has to be in kilograms for the math to work out. And after you do all the calculations, okay, if you take the time to check, everything will cancel so that your final answer will have units of meters per second. Okay, kinetic energy, talking about motion, essentially velocity. Velocity has a unit of meters per second. All right, this is going to be a calculation problem that you are going to do pretty regularly, and it will most certainly be on the AP exam, if not my quizzes and tests. The root mean square velocity. The root mean square velocity. Represented by mu r ms, that's root mean square over here. And we have 3RT, just like we saw in the average kinetic energy equation. However, we are dividing that term by the molar mass of the gas, again in kilograms, and then we are taking the square root of it, So it's the square root, okay? Root means square. Average, okay, mean, average equals mean, velocity. We're going to come up with a velocity at the end of this calculation. So root mean square, should be a velocity. The final units are in meters per second. All right, moving on to section 7, we have a couple of terms here for you to remember. A diffusion. Diffusion is the mixing of gases, so really fluids in general. But here we're talking about gases, so we'll keep it specific. Diffusion is the mixing of gases. We have effusion. Effusion describes the passage of a gas through a tiny orifice hole in an evacuated chamber, some sort of vacuum here. Also, I want you to remember that the rate of effusion measures the speed at which the gas is transferred into the chamber. Okay, moves the speed at which it moves through that hole into the vacuum. Yep, those don't work. Go technology. All right, so here we have a graphic in which we can see both diffusion and effusion. You can see that if I were to put a gas into this left-hand compartment and just let it go, it would spread out. Okay, it would spread out throughout this compartment until it was completely uniformly distributed throughout the compartment. So, if I were to put two gases in this compartment, notice that because of these gas particles simply zooming around, bouncing off the walls, hitting each other, bouncing off each other, until there's a uniform distribution of them, okay, on average, that both gases are actually going to do that. They're going to mix together. Okay, now, they're not going to be coming into contact in some insane way. They're simply going to be flying through space. Remember, these gas particles are so small compared to the distance in between them that the size of the particles is essentially zero. And so really when these two different kinds of particles would be mixing together, they're really not actually going to come into contact. They're really not going to be coming into contact. And so they'll just zoom past one another. And so they will quote-unquote mix together until they're both uniformly distributed throughout the chamber. That's diffusion. Now, effusion, so we have gas in this left-hand chamber, and we poke a hole, okay, in this dividing wall right here so that gas particles can move through. These gas particles are not simply going to be sucked in through this hole, like they're being sucked out of a breach in a spaceship here. These gas particles are going to continue to bounce around off the wall, bouncing down, up, this way, that way, down again, off of every wall until, by chance, they zoom in at such an angle that they actually do come through this hole. Okay. Now, the rate of effusion is how fast that these gas particles will actually move from this chamber and diffuse into this vacuum right here. Now, the faster the gas particles are moving, the greater the kinetic energy, the greater the velocity, the more collisions these things are going to have with the wall. And there's going to be more collisions with the wall, therefore more of a chance that one of these gas particles is going to hit the wall at this spot, making it able to go through the pinhole and actually move into the other chamber. So if the kinetic energy is up, meaning the temperature, then the rate of effusion will be greater. So that brings us to another law. This one is called Graham's law. It has to deal with effusion. Okay? And Graham's law states that the rate of effusion of two gases are inversely proportional to their molar masses square rooted. So we have the rate of effusion for gas 1 is equal to, notice how the molar mass of gas 1 is on the denominator because it's the inverse. Similarly, the rate of effusion for gas 2, okay, this being on the denominator, the molar mass of gas 2 is actually on the numerator because it is an inverse. What Graham's law does is it provides a comparison between the rates of effusion for two different gases. Okay, that's what Graham's law of effusion is. It's simply a comparison or a ratio. And you can see that the rate of effusion of a gas completely depends on the molar mass of the gas. Okay, larger the molar mass. I'm sorry, wrong thing. Moving on to chapter 5, section 8. Okay. Up until this point, we've talked about different gas laws. We've talked about the kinetic molecular theory of gases. We've given you 4 postulates of the kinetic molecular theory for gases. Turns out, none of those postulates actually happen in real life. Okay? In real life. An ideal gas is a hypothetical concept. No gas, absolutely no gas exactly follows all of those postulates for the kinetic molecular theory. So no gas exactly follows the ideal gas law. Therefore, if we're going to describe real gases, okay, non-ideal gases, we have to correct. We have to correct for that ideal gas law, Pivnert, okay, because it's not always exactly true. There are things that make the equation a little bit off and not exactly correct. So there are 2 situations in which gases behave extremely non-ideally, okay, very poorly, I guess you would say. One is when pressure is high. Gas particles are being squeezed together very greatly. And so what that means is you're actually making the gas particles come into contact with each other more often. Okay, they're hitting the walls of the container more often. Therefore, they're coming back and having a chance to collide with other gas particles more often. And remember, one of the postulates for the kinetic molecular theory is that there's no attraction or repulsion force in between 2 gas particles, and that's not always the case. But if those gas particles are very, very far away from each other, even if there is a little bit of an attraction force or a repulsion force, it's not actually going to change the path of that gas particle. But if you do make it so that those gas particles are crushed in towards each other, like when the pressure on the gas is high, you're going to make it more likely for those gas particles to be close enough to exert an attractive or repulsive force on each other. The second situation in which a gas is going to behave very non-ideally is when temperature is low. Because when temperature is low, kinetic energy is low, meaning the velocity of the gas particle as it zooms around is low. And so when two gas particles are moving past each other at a very, very high rate of speed, the attraction force or repulsion force needed to actually change the direction or change the path of the gas particle has to be pretty high. There has to be a pretty big attraction force or repulsion force to make those two things actually change direction. But if the temperature is low, the kinetic energy is low, therefore the velocity is low, they're going to be moving past one another for a greater amount of time. And so during that time, any small attraction or repulsion force that those two gas particles might have on each other, it's going to have more of an opportunity to operate and change the direction of that gas particle, make it curve towards or away or whatever it's going to do. All right. So, as a description of these real gases, okay, we've plotted PV over nRT, okay, and if PIV-NERT, if the ideal gas law is correct, and you divide PV by nRT, you're going to get a value of 1. You're going to get a value of 1. And what we've done here is we've plotted several gases over pressure, pressure to PV over nRT. And you see, if these were ideal gases, you would get just a straight line at 1. But that's not what we see. Okay, that's not what we see. We see that these gases start to get very far away from this line at these high pressures. Okay, at high pressures, these different gases get very, very far away from this ideal gas line, which is a graphical or numerical way to say that when pressure becomes very, very high, gases tend to not behave ideally. All right, so for this graph, what we've done is we've taken nitrogen gas and we've plotted its behavior at 3 different temperatures, okay? 203 Kelvin, 293 Kelvin, and 673 Kelvin, 3 different temperatures. Okay, and we have the same idea here. We have pressure on the x-axis and PV over nRT plotted on the y-axis. Again, if you have an ideal gas behaving perfectly ideal, this value is going to be 1. Now you can see that at very, very low pressure, okay, or essentially no pressure in a perfect vacuum, that nitrogen is going to behave pretty ideally. But as pressure increases, we start moving away from this, this perfection point here. And let's not get caught up in this, this bowing down. We're not going to talk about that too much. What we want to pay attention to is, notice that the colder temperature, 203 Kelvin, moves away from ideal behavior faster than the other 2 temperatures. And the higher temperature, 673 Kelvin, remains closer to ideal behavior than the other 2. Okay? Because again, at low temperatures, gases begin to behave less and less ideally. So this low temperature, okay, which is about negative 70 degrees Celsius, just FYI. This nitrogen gas is going to behave very not ideally. Okay, but this nitrogen gas at a very high temperature, is going to behave more ideally. It's not going to be perfect, but it will behave more ideally, even as it does move away from this 1.0 ideal gas line. All right, so it is true that there is no such thing as an ideal gas. It's a hypothetical concept. No gas behaves ideally. Why, you ask? Well, because the universe hates you, that's why. But if we're going to describe what real gases behave like, we have to make some corrections or adjustments to our ideal gas law. And so what we actually have here is the ideal gas law with some corrections. Now, your book goes through a huge explanation, several pages, describing how these corrections were made mathematically. Those are not things that you're going to need to back up. Okay, the mathematical derivations of this corrected real gas equation using the van der Waals equation, that's not something you're going to have to do. Now, you might have to take this equation and do some plug and chug. Okay, take some values and solve for some term in here. But in terms of explaining the derivation, that's not something you're going to have to do. But what we've done here is we've taken the PV equals nRT, and in order to make it correct, we've had to make some adjustments. Okay, this is the ideal pressure. This is P. Okay, and this is V. We've taken the P ideal, and we've noticed that the observed pressure is different from the ideal pressure. This is observed pressure, and we have to add some adjustments here. And we have to take the ideal volume and then make some adjustments here. Now, once we've done that, we can have the PV equals nRT and have it correct, but not until then. And again, that's because no gas in real life behaves like an ideal gas. And specifically for real gas, the actual observed pressure is lower. It's actually less than the pressure expected for an ideal gas due to the intermolecular attractions and repulsions that occur in real gases. Okay, remember that was one of the postulates of the kinetic molecular theory for gases, is that there are no attraction or repulsion forces between two gas particles. Well, that always happens. There's always an attraction force or a repulsion force, whether it's simply like polarity, or you have some electrostatic attraction between partially charged sides of a gas particle. There's always something going on there. And so that's a postulate that can never actually be carried out. In fact, none of those postulates can be perfectly carried out ever. Okay, so we have to adjust pressure here. And how we're going to do that, if you go back to that van der Waals corrected gas law equation, there's an A value and a B value. And the value of A reflects how much of a correction must be made to adjust the observed pressure up to the expected ideal pressure. Because remember, the observed pressure of a gas is less than the expected value for pressure for an ideal gas. So we're going to have to throw in an extra term, okay, A here, A. And the smaller that A term, the smaller that term is for A, that indicates that there is very little intermolecular attraction or repulsion in between those gas particles, those gas molecules. And so the observed pressure is actually a lot closer to the ideal pressure. Now, it's just never going to be exactly the ideal pressure, but it's going to be a lot closer. Notice on the table 5.3, these are the van der Waals constants for some gases that I'm sure you've heard about. Notice those first two gases up there. That's helium and neon. Those are noble gases, things that are fairly inert. But if you go all the way down to the bottom, you see water, which is polar, and then kind of bottom 2/3 there's chlorine gas, which is very, very reactive. It's got a pretty high value itself. And so you can see that when there's a polar particle like water, there's going to be a lot of intermolecular force attractions between water molecules and other molecules around it, and so you're going to have to adjust that observed pressure, okay, up to be to equal the ideal pressure. Same thing with the B value here. We're talking about the volume for something here. All right, that is going to do it for this video lecture here. Look back in a little while. I'm going to try to put a supplemental video up working out some problems, so hopefully you can get some help if you need it there. All right, I will see you next period.